ในส่วนต่อไปเดี๋ยวอาจารย์จะให้อาจารย์เดนเนียลเป็นคนอธิบายในส่วนของภาคภาษาอังกฤษให้นักศึกษานะครับผม
These have quite a lot to do with industrial electrics. When you're working in industrial, you will find certain things will need to run with ferromagnetic metals, etc. So first of all, let's wake everybody up. Everybody, I just want to hear you say ferromagnetic.
Ferromagnet.
Nice, good job, guys. Well done. So ferromagnetism or ferromagnets. Some substances exhibit strong magnetic effects called ferromagnetism. So this substance, ferromagnetics, it causes strong magnetic effects. So some examples of ferromagnetic materials are
iron.
Good job. So iron is a ferromagnetic metal, okay, material. Well done. Number 10, Ford.
Cobalt.
Yeah?
Yeah.
Cobalt. Okay, that's another type of ferromagnetic material. Number 12. Okay, please read this.
Nickel.
Good job. Nickel. That's another ferromagnetic material. Okay, 11. Bogey.
11.
11. Oh, it's 11's you. Sorry. All right. Okay, try this one.
Gadolinium.
Again.
Gadolinium.
Nice, good job. Well done, mate. Gadolinium.
Thanks,
Nice.
teacher.
Good. Okay. And let's have Bogey. Are you there?
Boogie, wow.
Bogey. But okay. Can you read this one? It's so hard.
Diaphragm.
Dryprosium.
Dryprosium.
It's good. It's close. If we have just the prosium, you got that right. Prosium. Yeah. So you'd say dice. Dice-prosium. Yeah.
Dysprosium.
Nice. Good job. It's not something you would work with especially. The main that you will see during your electrical career will be iron and maybe nickel. Okay. There's a couple more. But you will learn this as you go. So they contain permanent, which means constant, no stopping, atomic magnetic moments that tend to align parallel to each other, even in a weak external magnetic field. So they will remain permanent. Okay, they will remain magnetic. You can't really turn it on or off. Kaljai Mai?
Yes.
Yeah. Okay. Okay, I'll quickly read this for you. Ferromagnetism. Okay, this is what we call the process in which ferromagnets work. So ferromagnetism refers to the phenomenon by which ferromagnetic materials, like what we have spoke about here, so iron, cobalt, nickel. So iron, nickel, cobalt, and certain alloys become magnetized in a magnetic field and retain their magnetism when the field is removed. Okay, so basically they remain magnetized. When our magnetic field is removed, they will still remain magnetized. It's confusing to explain this in English. Here's some more ferromagnetic metals. So we have iron, cobalt, nickel, gadolinium. Okay, let's get number 14. Tipsy.
You well, hello,
you there? All right.
Yeah, teacher.
Hey, buddy, can you read this?
Neodymium.
Give it a try. Neodymium, yeah? Or not danium, neodymium.
Neodymium.
It's a really hard word to say. Yeah?
Neodymium.
Even I'm struggling. So neodymium.
Neodymium.
Okay, it sounds like an N, but it's not.
Neodymium.
Neodymium.
Yeah, so if we go neo, we know this.
Neo
D,
dia
neon.
Neom.
Neodymium.
Neodymium.
Nice, okay, good, well done. It's
Yes.
really hard to say. Good, well done guys, nice one. And number, let's have 12, Sipsong.
Wow. Yeah.
You there, all right. Please read this.
Ferromagnetic ceramic.
Nice, good job, well done. Thank you, ferromagnetic ceramics, okay. Nice, good. Okay, here's a couple of examples. Transformer, big transformer. It's normally a mains distribution. Okay, and then smaller transformers up here, which are used for small alarms or bells, small motors, whatever. So like I say, we use the symbol L for inductance. In honor of the physicist, okay, the SI system, the measurement for inductance is Henry. Inductance. With the unit symbol H, named in honor of Joseph Henry, who discovered inductance independently of, but not before, Michael Faraday. Okay, like this. So these are different schematic symbols here of an inductor. This side we have an air core inductor. Remember we spoke about this at the start. An air core will mean the core is plastic. An iron core inductor, yeah, the core is iron. Ferrite core inductor, the core will be a ferrite, and a variable core inductor. Okay.
Yes.
This is what the inside of, let's say, a big transformer looks like. Easier to say a big one. We have two sides, primary and a secondary side. Okay. Inside we have a transformer oil. Yeah. These can act as inductors, and it also keeps the heat down. So it stops it from overheating so much. The radiator tube for heat dissipation is what we call. Okay, nice and simple. Let's look at two different types of transformers we can get. Okay, so I want to say 23.
P13
not have any reason.
Or not have here. 16.
Yeah, teacher.
Hey, buddy. What does this say up here?
อันนี้อ่านใช่ไหม
ใช่
Step up transformer.
Nice, good job. This is a step-up transformer, which basically means our voltage input, let's say, could be 220 volts, which will feed our primary winding. And then there's a big thing that happens here with magnetic flux and a magnetic field. But on this side, the secondary coil, our voltage has gone up, okay? So we could have gone from 220 volts to 400 volts, let's say. So an input of 220 volts, output of 400 volts, and then that can be sent wherever it's going to go, okay? Or we could have, let's say, 120 volts, comes out at 220 volts. And then we can have that going to anything we want to feed in our house. Not that you would use a step-up transformer. So what we would do is the input voltage to our primary coil would be smaller, less windings. Our secondary coil, more windings, gives us more voltage on the output. going to show you in a minute what I mean. Okay, and number 6 or number 5. Number 8. Oh, I've had number 8. Number 9.
Bobby.
Hi.
Bobby.
I'm here, teacher.
Okay, buddy. What does this say up here?
Step down transformer.
Okay, good, thank you. So, Bogey, if it's the opposite to a step-up transformer, if we put 200 volts in here, will it come out more than 200 volts or less than 200 volts on this side? So 200 volts in here, step down transformer, more than 200 volts here or less than 200 volts? Which one?
Fail.
ไม่อะ
เราถามว่าไอ้ step down transformer เนี่ยถ้าใส่เข้ามันจะเปลี่ยนจากไฟฟ้าตัวที่เข้าไปมากขึ้นหรือลดลง
อ๋อ ดาว
Nice. So less, yeah?
นั่นแหละ
Nice. Good job. Well done. Well done. Nice one, buddy. So we can look at it like this. This is our power supply. Yeah. This is our primary winding. So our supply input. So we'll have our live and our neutral here, yeah, from our power source. And then there'll be big magnetic field and magnetic flux physics happening here. Then we come to our secondary winding, to our output, to our load. In this case, a motor. More windings would mean a step up, yeah, transformer. If we understand, I'll tell you what, I'll do this. This will be easier. All right, so here we have a transformer, yeah? We have our power supply, a transformer. Now we can control our number of turns. So we can have on our primary coil, this side, if we have 1 and 1, so it's even, 1 turn on our primary, 1 turn on our secondary, we have 220 volts into our primary, ratio 1 to 1. How many volts on this side? Any guesses? So we have 219 volts here, about 220, yeah? On our multimeter here, reading volts. Goes through our transformer, so this side of the winding, and then out of our secondary winding. And it's 1 to 1, so it's the same, 219. Now we can change this. 10, right. So now we've got 10 windings, 10 turns on our primary side, 5 turns on our secondary side, which means it will be half of this, 10 to 5. 5 is half of 10. What's half of 220 divided by 2?
110.
Good job. So now when we press play, we should have 110 volts at our load side. Close enough too. So this is what a transformer does, yeah? The inductor, so it'll come in, take voltage from high voltage to low voltage, or low voltage to high voltage. Because we could change our values now. And if we put on our primary winding 5 coils, on our secondary winding 10 turns, who can guess whether our voltage is going to be higher or lower on this load side?
Be higher.
Good. What? Because of our ratio, yeah? A number of turns on the secondary and primary.
Yeah. Yes.
So this is then called what type of transformer?
Step up.
Step up. Nice, good. Okay, that's the basics of transformers. Very, very basic. Turns ratio. This is the number of turns in the primary to the number in the secondary. So let's just do one thing. If we had, let's say, 100 turn-ins here on our primary side, 50 turn-ins, 50 turns on our secondary side, we're going to have 220 volts into our primary winding. Out of our secondary winding to here, to our load, what voltage are we going to have?
Oh, shit.
We've got a ratio of 100 to 50.
150. Yes. What the hell?
Hard one to figure out. Because it's half. It's still half, yeah?
Still half of it.
It's 100.
110.
It's still only half of 100. Yeah? So what if we went like this? 1,000 turn-ins, which you wouldn't want to normally see. 1,000 turn-ins in our primary coil, 500 in our secondary coil, 1,000 turns here, 500 turns on our secondary. At our load, what is our voltage?
Like 110.
Look at the ratio.
Like cut it to a half.
So we're still half, yeah?
Yes.
Yeah?
Oh, right.
So if we're coming in at a high voltage here, inside between our inductors, our windings, and we come out at 109 volts or 110,
Volt.
is it a step up or step down?
Step down.
Yeah.
Good, because we've gone from high voltage to low voltage. Now, if we swap this around and we go 500 turns on our primary,
Fails.
1,000 turns on our secondary, is it going to be a step up or a step down transformer?
Step up.
Yeah, so the voltage is going to be higher at our load end than it is at our primary end, yeah? What's the voltage going to be?
About 440, right? Like this, maybe.
Very good, very, very good. So you know your ratios, easy ratios. Now let's have a bit of fun.
Hey.
Oh no, that's 23, yeah. You guys are going to have to work this out.
Oh.
So we got 250 turns on our primary side, 23 turns on our secondary side. We got 220 volts supply to our primary winding. Okay, just go like this. You press play. So we have 220 volts to our primary. Our secondary windings come out to our load. What's our voltage at the load?
Is that 11?
11?
Maybe.
Let's see what you got. 20.
20, yeah.
Yeah, a ratio of 254 to 23 is 20. Yeah. So, Kaujai Mai, step up, step down, easy to understand.
Uh-huh.
Yes.
Where were we?
Okay.
And then I've just showed you the turn ratio from secondary to primary or primary to secondary. NP, N means number of turns, P means primary. So NS, what does NS mean?
Yes. Number of turn in the secondary.
Good, in the secondary winding. P for primary, S for secondary, N for number of turns. Now we have a voltage ratio. The ratio of primary voltage to secondary voltage is known as voltage ratio. So what we looked at here, our primary was 220 volts, and our secondary, in this case, was 20 volts, let's say. So that's our voltage ratio. This is calculated like this. Voltage primary divided by voltage secondary equals number of turns on the primary side divided by number of turns on the secondary side. So VP, voltage in primary, VS, voltage in secondary, and then we know our numbers of turns in primary, number of turns in secondary. Okay? So current ratio. So it's the same as the turns ratio, voltage ratio, as in numbers, but now it's the current. Yeah? It's the inverse of the voltage ratio. So what we do is current secondary winding divided by current primary winding equals, so this is what we want to find the answer to, voltage primary divided by voltage secondary. Okay?
Okay.
Types of cores. Okay, everybody together. 3, 2, 1. Air core.
Air
Air
core.
core.
Number 8.
Number 8
นี่
นี่คนเดิม
ครับ
Okay. What does this say, Nee? Please read. Air core. Nice, good job. What does this say, Nee? What? I don't know what's going on with my computer. Nee, please read this.
laminated เหรอ
Good, nice job.
Net core.
Really good. Thank you, Nee. So we have an air core like this. It's the simplest inductor. Plain, straight lengths of wire in turns. So it's in a coil. We'd say 1, 2, 3, 4, 5, 6, 7. This has 7 turns. Yeah. And then we have a laminated core. So these are core materials formed by arranging many number of laminations on top of each other. Yeah. Here you'll see lots of laminations like this that builds our core. These laminations may be made of different materials with different thicknesses. So it could be this thick, could be this thick, could be this thick. Okay, number 15, Sipa. Okay, I think we're running out of time, so let's just all together.
Ferriodo.
Try again.
Ferriodo.
Toradal.
Ferriodo.
Toradal inductor.
Ferriodo. Ferriodo.
Toradal inductor.
Doctor.
Yeah. I'd like to say wire wound on a core which has a ring or donut-shaped surface. So this is our wire around a core. We'd call this the core. Okay.
Toroidal.
Ferrite cores. Ferrites are synthetic ceramic materials, as you see here. Okay. They are ferromagnetic. They provide high values of flux density for our magnetic flux that we use inside transformers. They're like iron, but have the advantage of being insulators. Yeah. Nice. Variable inductor. Here we go. Schematic symbol, this. What it actually looks like, I'll give up with this computer, I really do. What it looks like is this. Okay? See, it's got a handle on the side. So a coil whose effective inductance can be changed. Using the handle. Good. Variable. Gives it the name, variable. You can change it to various inductance. Also known as a variable inductance. Nice and easy. Troubles in coils. So problems that you can come across. Direct current resistance of a coil. A coil has DC resistance equal to the resistance of the wire used in the winding. The amount of resistance is less with heavier wire and fewer turns. Number 2, open coil. An open winding has infinity resistance, as indicated by an ohm meter reading. Yeah. So if you test, let's say, windings or whatever, and you have an infinity reading, you know that it's an open coil. I'll give up with this computer, I really do. I don't know what it's doing. Number 3, value change. the value of an inductor can change over time because of core breakage, windings relaxing, or shortened turns. So over time, so let's say it's made 20 years ago. Now, after 20 years, values can change because it's old. That's basically what it's saying. Things happen when they get old. Number 4, short across. In this case, excessive primary current flows as though it were short-circuited, often burning out the primary winding. Short circuits aren't good. Troubles in cores, here we go. I can't understand that, it's in time, but you can see there's a break here. Yeah, so it's an open coil. Here it's shorted. Okay, and this is good. You can see the short at the bottom. Let's go down. Very quickly do this. So to find inductance total on a series circuit, here we go. Series circuit. We want to find the total inductance, like what we've done with capacitors in the past and resistors. This time, we want to find inductance total. So on a series circuit, just add it all together. Yeah, same with the resistors in a series circuit. L1 plus L2 plus L3 plus blah, 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 plus Ln. So in this case, 1 Henry plus 2 Henry plus 1.5 Henry plus 5 Henry gives us, what's the answer?
9.5 Henry.
Good. So our LT, our inductance total, is 9.5 Henry. Nice and easy. Okay. Blah, blah, blah. Same again. Okay, L1, L2, L3. So 5 microhenry. This is where it changes a bit. 2 microhenry, 10 microhenry, plus 1,000 millihenry, sorry. 5 millihenry, plus 2 millihenry, plus 10 millihenry, plus 1,000 microhenry. Yeah, so we do the sum as thus. LT, inductance total, 5 plus 2 plus 10 plus 1 millihenry. And it gives us the answer of, what's this?
18 millihenry.
Good job. So we got an inductance total of 18 millihenry in this series circuit. Let's look at parallel. Okay. We know this. Resistors the same. We use the same concept in resistors in the parallel circuit. 1 divided by inductance total, LT. So 1 divided by L1 plus 1 divided by L2 plus 1 divided by L3, so on, so on, so on, until 1 divided by Ln, your final one. So inductance total would be L1 multiplied by L2 divided by L1 plus L2. And we all know how to do this. So we've got 10 in our L1. In our first inductor, we have 10 millihenries. In our inductor 2, we have 5 millihenries. Inductor 3, 2 millihenries. Okay. So to find out our inductance total, it's 1 divided by inductance total equals 1 divided by L1 plus 1 divided by L2 plus 1 divided by L3. In this case, 1 divided by 10 equals 1 divided by 10 is
10.
10. 1 divided.
Okay, 1 divided by 5 is
5.
1 divided by 2 is
2.
yeah. But here we got 1 divided by 10.
With 10. 1 with 10, right? And 1.
1.
Oh! Okay. 1.
Are we sure? Okay, so anyway, we come down to 1 plus 2 plus 5. So LT is 1 plus 2 plus 5. divided by
10.
10. Yeah? And then, so 1 divided by LT, 8 divided by 10, means then we're going to find our inductance total, 10 divided by 8,
8.
and our inductance total is
1.25 millihenry.
millihenry. Okay, good job. And this, so we could say this is a compound circuit. L1, we have 10 millihenry. L2, 10 millihenry. L3, 15 millihenry. L4, 5 millihenry. I'm not going to go into whatever the question is for this, just as long as you know our L's are for our inductors. Any questions? Some of that might have been confusing.
มีข้อสงสัยตรงไหนเนาะทีนี้ก่อนที่เราจะออกไปทำการแข่งขันเดี๋ยวอาจารย์มีคลิปวิดีโอนำเสนอในเรื่องของการทำงานของตัวเหนี่ยวนำเนี่ยให้นักเรียนเห็นภาพมากขึ้นนะครับ
or electromotive force refers to the voltage created by a battery or by a changing magnetic field. Counter EMF, also called back EMF, is a related phenomenon that we will illustrate in this animation. Here is a simple circuit featuring a battery, a knife switch, and a light bulb. This circuit also contains a wire coil that serves as an inductor. Inductors store energy in the form of magnetic fields that are generated around them when a current passes through them. They are called inductors because they induce a voltage in their coils when that magnetic field changes. We will see this in a minute. The elements in this animation are not represented to scale, and the action we will show in super slow motion actually takes place in the blink of an eye. But this animation is helpful for illustrating how back EMF works. When we power this circuit, the electrons in the current create a magnetic field around the wire as they move through it, as shown by these blue arrows. If the wire is formed into a coil, like this inductor, the magnetic field lines converge in the center. They gradually build up to a maximum magnetic field that is much stronger than the one around the straight length of the wire. Let's watch this again, but this time we'll pay closer attention to what's happening in the wire conductor. In this parallel circuit, the current can travel either through the inductor or through the light bulb. When the current reaches this junction, it splits and flows to both the inductor and to the light bulb. At first, the current flows much more strongly towards the light bulb. This happens because as the magnetic field in the inductor grows, it induces its own voltage through Faraday's law. This is called electromagnetic induction. So the inductor here is creating a back EMF represented by this yellow arrow. Back EMF always opposes the change that created it. So in this instance, the back EMF is opposing the change created by turning on the circuit. It opposes the current. The result, as you can see, is that the back EMF effectively diverts the current away from the inductor and toward the light bulb. This causes the bulb to light up, but only briefly. Once the magnetic field around the inductor reaches its maximum field, the back EMF fades, and the current now favors the path through the inductor because the bulb creates some resistance to the current. The same phenomenon occurs when the magnetic field is shrinking, which happens when we open the switch and stop current flow from the battery. Once again, the back EMF opposes the change that created it. In this case, the change is the cessation of current. So, opposing this change, the back EMF wants to maintain the current, which flows once again to the bulb, causing it to flash before it fades away altogether.
ในตัวนี้ก็จะเป็นการอธิบายเกี่ยวกับ back EMF back EMF ก็คือสภาวะของการเหนี่ยวนำเสร็จแล้วก็จะมีการสภาวะก็คือการ ไหลย้อนกลับของการเหนี่ยวนำนะครับ อย่างเช่นว่ามีการเก็บประจุเขาเรียกว่าการเหนี่ยวนำของตัวอินดักเตอร์แล้วเนี่ยเมื่อมันถึงการเหนี่ยวนำถึงจุดหนึ่งแล้วเนี่ยถ้าเกิดว่าเรามีการออฟสวิตช์หรือปิดวงจรไปเนี่ยมันก็จะมี back EMF หรือว่าการเหนี่ยวนำไหลกลับเข้ามาสู่วงจรได้เหมือนกันนะครับผมทีนี้เดี๋ยวเราไปดูนะครับตัวนี้ก็จะเป็นว่าการทำงานของพวกอินดักเตอร์เนี่ยยังทำงานยังไงนะครับผม
Guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at inductors to learn how they work, where we use them, and why they're important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. So what is an inductor? An inductor is a component in an electrical circuit which stores energy in its magnetic field. It can release this energy almost instantly, and we'll see how it does that later on in this video. Being able to store and quickly release energy is a very important feature, and that's why we're going to use these in all sorts of circuits. Now, in our previous video, we looked at how capacitors work. Do check that out if you haven't already, links down below. So how does an inductor work? I want you to first think about water flowing through some pipes. There is a pump which pushes this water, and the pump is equivalent to our battery in the circuit. The pipe will split into two branches, and the pipes are equivalent to our wires. One branch has a pipe with a reducer in it, and that reduction makes it a little harder for water to flow through it. So the reducer is equivalent to resistance in our electrical circuit. The other branch has a water wheel built into it. The water wheel can rotate, and the water flowing through it will cause it to rotate. The wheel is very heavy though, so it takes some time to get it up to speed, and the water has to keep pushing against this to get it to move. This water wheel is going to be equivalent to our inductor. When we first start the pump, the water is going to flow, and it wants to get back to the pump as this is a closed loop. This is just like when electrons leave the battery, they flow and try and get back to the other side of the battery. By the way, in these animations, I use electron flow, which is from negative to positive, but you might be used to seeing conventional flow, which is from positive to negative. Just be aware of the two and which one we're using. So as the water flows, it reaches the branches and has to now decide which path to take. The water pushes against the wheel, but the wheel is going to take some time to get moving, and so it's adding a lot of resistance to the pipe, making it too difficult for the water to flow through this path. Therefore, the water will instead take the path of the reducer because it can flow straight through this and get back to the pump much easier. As the water keeps pushing, the wheel will begin to turn faster and faster until it reaches its maximum speed. Now, the wheel doesn't provide almost any resistance, so the water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer, and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia. As it keeps rotating, it will now push the water and act like a pump. The water will flow around the loop back on itself until the resistance in the pipes and the reducer slows the water down enough that the wheel stops spinning. We can therefore turn the pump on and off, and the water wheel will keep the water moving for a short duration during these interruptions. We get a very similar scenario when we connect an inductor in parallel with a resistive load such as a lamp. This is the same circuit as we just saw, but I've just wired it more neatly. When we power the circuit, the electrons are going to first flow through the lamp and power it. Very little current will flow through the inductor because of its resistance at first is too large. The resistance will reduce and allow more current to flow. Eventually, the inductor provides nearly no resistance, and so the electrons will prefer to take this path back to the power source rather than through the lamp, so the lamp will turn off. When we disconnect the power supply, the inductor is going to continue pushing electrons around in a loop and through the lamp until the resistance dissipates the energy. So what's happening in the inductor for it to act like this? Well, when we pass electrical current through a wire, the wire will generate a magnetic field around it. We can actually see this magnetic field by placing compasses around the wire. When we pass a current through the wire, the compasses will move and align with the magnetic field. When we reverse the direction of the current, the magnetic field reverses, and so the compasses will also reverse direction to align with this. The more current we pass through the wire, the larger the magnetic field becomes. When we wrap the wire into a coil, each wire again produces a magnetic field, but now it will all merge together and form one large, more powerful magnetic field. We can see the magnetic field of a magnet just by sprinkling some iron filings over the magnet, which will reveal the magnetic flux lines. When the electricity supply is off, no magnetic field exists. But when we connect the power supply, current will begin to flow through the coil, so a magnetic field will begin to form and increase in size up to its maximum. The magnetic field is storing energy. When the power is cut, the magnetic field will begin to collapse, and so the magnetic field will be converted into electrical energy, and this pushes the electrons along. In reality, it's going to happen incredibly fast. I've just slowed these animations down to make it easier to see and understand. So why does it do this? Well, inductors don't like changing current. They want everything to remain the same. When the current increases, they try to stop it with an opposing force. When the current decreases, they try to stop it by pushing electrons out to try and keep it the way it was. So when the circuit goes from off to on, there will be a change in current. It has increased. The inductor is going to try to stop this, and so it creates an opposing force known as a back EMF, or an electromotive force. This back EMF opposes the force which created it. In this case, that's the current flowing through the inductor from the battery. Some current is still going to flow through though, and as it does, it generates a magnetic field which will gradually increase. As it increases, more and more current will flow through the inductor, and the back EMF will eventually fade away. The magnetic field will reach its maximum and the current stabilizes. The inductor no longer resists the flow of current and acts like a normal piece of wire. This creates a very easy path for the electrons to flow back to the battery, much easier than flowing through the lamp. So the electrons will flow through the inductor and the lamp will no longer shine. When we cut the power, the inductor realizes that there has been a reduction in current. It doesn't like this and tries to keep it constant, so it's going to push electrons out and try to stabilize it. This will power the light up. Remember, the magnetic field has stored energy from the electrons flowing through it, and it will convert this back into electrical energy to try and stabilize the current flow. But the magnetic field will only exist when the current passes through the wire, and so as the current decreases from the resistance of the circuit, the magnetic field collapses until it no longer provides any power. If we connected a resistor and an inductor in separate circuits to an oscilloscope, then we can visually see the effects. When no current flows, the line is constant and flat at zero. But when we pass current through the resistor, we get an instant vertical plot straight up, and then the flat line continues at a certain value. But when we connect an inductor and pass current through it, it will not instantly rise up. It will gradually increase and form a curved profile, eventually continuing at a flat rate. When we stop the current flowing through the resistor, it again instantly drops and we get this sudden vertical line back down to zero. But when we stop the current through the inductor, the current continues and we get another curved profile down to zero. This shows us how the inductor resists the initial increase and also tries to prevent the decrease. By the way, we've covered electrical current in detail in a previous video. Do check that out, links down below. What do inductors look like? Inductors in circuit boards will look something like this. Basically just some copper wire wrapped around a cylinder or a ring. We do get some other designs which have some casing over. This casing is usually to shield the magnetic field and prevent this from interfering with other components. We will see inductors represented on engineering drawings with symbols like these. Something to remember is that everything with a coiled wire will act as an inductor. That includes motors, transformers, and relays. So what do we use inductors for? We use them in boost converters to increase the DC output voltage while decreasing the current. We can use them to choke an AC supply and only allow DC to pass. We can use them to filter and separate different frequencies. And obviously, we also use them for transformers, motors, and relays. How do we measure inductance? We measure the inductance of an inductor in the unit of Henry with a capital H. The larger the number, the higher the inductance. The higher the inductance, the more energy we can store and provide. It will also take longer for the magnetic field to build, and the back EMF will take longer to overcome. You can't measure inductance with a standard multimeter, although you can get some models with this function built in, but it won't give you the most accurate results. That might be okay for you, it depends what you're using it for. To measure inductance accurately, we need to use an RLC meter. We simply connect the inductor to the unit and it will run a quick test to measure the values. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to